This is the first of two lessons in which we're going to take a look at exponential equations and graphing them. In this first lesson, we're going to take a look at the basic exponential function, y equals a times b to the x. In the second lesson, we're going to take a look at that same thing, but with vertical and horizontal shifts added to it. But in order to get a basic understanding and working knowledge of how exponential equations work, we're going to ignore the vertical and horizontal shifts at this point and just take a look at this basic exponential function. So you'll notice in this basic exponential function here, we have y equals a times b to the x. A couple things to note about this. Number one, my independent variable x is an exponent. That's the piece that makes this type of equation unique from the other type we've looked at, namely linear equations, quadratic equations, polynomial equations. All of those, the independent variable x was in the base section of the equation. Here, our variable is an exponent, so it's our exponent that's changing all the time in order to determine our dependent variable y. Now we have two constants here, a and b. A we call our initial value. A, believe it or not, is our y-intercept. B we call our base multiplier. As we graph some of these, you're going to see how this comes into play and why we call the value of b our base multiplier. Now a couple restrictions really quick. A cannot equal 0. If a equals 0, our entire function equals 0 because everything is multiplied by a. Two other pieces of restriction that we have on the value of b is that b must be greater than 0. We're not going to take a look at negative b values. And also, b cannot equal 1. If we have b equals 1, we have a constant equation that is essentially a horizontal line at the value of a. So let's go ahead and take a look at what happens and what an exponential equation ends up looking like. So our first example here is y equals 3 times 2 to the x. If I compare that to y equals a times b to the x, we can see that our value of a is 3 and our value of b is 2. Now what's nice is because we know that a is our initial value or y-intercept, I can look at my value of a, which is 3, and I know that's the location that my graph crosses the y-axis. So at y equals 3, I'm going to go ahead and put a point because I know that my graph crosses through that point because that's my value of a, my y-intercept. Now to get the rest of the graph, we're simply going to construct a t-table. I want to see what the left-hand side and right-hand side of that looks like. So I know my y-intercept is at the point 0, 3, right? My x value of this point is at 3, and it's at 0, and the y value is at 3. So I'm going to pick a negative 1 and a negative 2. I'm also going to pick a 1 and a 2 and a 3. I'll actually pick and squeeze a negative 3 in here as well. So these are the values that we're going to plug in for x. Okay, our calculator up. Okay, so let's start with the negatives. Negative 3. So we need to do 3 times 2 to the negative third. And I'm getting a 0.375. Now I'm going to do 3 times 2 to the negative 2. And I get a 0.75. Now a 3 times 2 to the negative 1. We get a 1.5. We already know that if we plug in 0, we're going to get 3 because that's our y-intercept from our value a. Let's plug in 1. 3 times 2 to the first power is 6. Now if we plug in value of 2 for x, that's 3 times 2 squared, which is 12. And last but not least, let's do 3 times 2 to the third power. That is a 24. Okay, so a couple things. Before we take a look at those things, let's go ahead and plot these points. I know I've got 0, 3, 1, 6, 2, 12, and 3. This goes up to 19. Here's 20, 21, 22, 23, 24, 324 as our other point way up there. And then we also have negative 1, 1.5, negative 2, 7.5, and negative 3, 3.75. A couple things that we need to notice about this as we observe what this function does is this. I mentioned the base multiplier and that we would see how that comes into play. Here's where we're going to see it come into play. If we take a look at the t-table that we constructed, let's start at the x value of negative, we'll just start at the x value of negative 3. If I look at the x value of negative 3 and I multiply it by my base multiplier of 2, what do I end up with? I end up with 0.75. If I multiply that by my base multiplier of 2, I end up with 1.5. If I multiply that by my base multiplier of 2, I end up with 3. If I multiply that by 2, I end up with 6. If I multiply that by 2, I end up with 12. If I multiply that by 2, I end up with 24. So your base multiplier actually sets the pattern that you end up seeing in your equation. Now there's a couple things that are critical about that. Okay, number one, you'll notice that we only observe that pattern because we are counting by 1s in the x. If I were to count by 2s in the x column, we would not see that pattern of each consecutive one being multiplied by 2. And we only see that because in my x column, we're counting by 1s. The other piece that's important about this is that we can actually go backwards, but instead of multiplying by 2, we divide by 2. 24 divided by 2 is 12, divided by 2 is 6, divided by 2 is 3, divided by 2 is 1.5, divided by 2 is 0.75, divided by 2 is 0.375. Now the significant piece about that is this. If I keep dividing by 2 over and over and over again, what does the rest of my equation look like down in this region of the graph? Well, if I have a positive number that I'm dividing by 2 over and over and over again, the question is, will I ever get to the value of 0? And the answer is no, I will never get to the value of 0. And so in that case, what we have is this. If I look at my graph, I know I'm coming down from way up high here, coming down through that point, through that point, through that point, coming down through here, and I know that I'm going to slowly just level off right at my x-axis, because if I just keep dividing my y values by 2, I'll never actually get to a y value of 0, which means we're always going to stay above the x-axis. So this is what the general shape of a exponential equation looks like. It's called an exponential curve. It has a leveling off point at the x-axis, and it increases what we call exponentially. So let's go ahead and take a look at another example to drill some of these concepts home, and also to view the other type of exponential equation that we will end up seeing. So in this equation, if we compare it to y equals a times b to the x, our a value is 16 and our b value is 1/2. So we know that our a value represents our y-intercept. So up at y equals 16, I am going to plot a point. And then from that, what I'm going to do is I'm going to, again, build a t-table. But I'm going to not build a t-table on both sides of this point, 0, 16. I'm only going to look at values greater than x equals 0. You'll see why I do that in a moment. So let's look at 1, 2, 3, and 4. Getting our calculator back up here. Okay, we need to do an x value of 1. So that's 16 times 1/2 to the first power. We end up with 8. Now we need to do 16 times 1/2 to the second power, and we end up with a 4. We do 16 times 1/2 to the third power. We end up with a 2. And last but not least, let's do 16 times 1/2 to the fourth power. We end up with a 1. Now, you might be seeing the pattern here in that our base multiplier here is a half. So every time I move from one x value to the other, what's happening to my y value? It's being multiplied by a half. 16 times a half is 8. 8 times a half is 4. 4 times a half is 2. 2 times a half is 1. So if I plug in an x value of 5, following that pattern, 1 times 1/2 is 1/2. And we could keep that pattern going. Let's fill this in and see what happens. 1, 8 is here. 2, 4. 3, 2, 4, 1, 5, 1.5. Now the same principle here works. If I keep multiplying by 1/2 over and over and over again, will I ever get to 0 on my y's? And the answer to that is no. So again, I have a situation here in which I level off right at my x-axis because of how the exponential equation works. It's multiplying by my base multiplier. And if you're multiplying by a positive, if you're multiplying a positive by a positive over and over and over again, you'll never actually get to 0. It's always going to stay above, but it's going to get really, really close to 0. Now you'll notice that this one actually acted opposite of the other one. Instead of starting low and going high in this case, so starting low and going high, we have a situation in which we started high and we went down low. That's why I didn't look at any of the left-hand side of my y-intercept, because I know it just increases quite significantly on that left-hand side off the graph. The reason I knew I was going to get that is that my base multiplier was less than 1. Okay, so let's talk about that really quick. We see two different types of exponential equations happen. We call those two types growth and decay. We have a growth scenario when our base multiplier is greater than, not 0, greater than 1. If my base multiplier is greater than 1, that means I'm multiplying by something greater than 1, which means my values are always going to get bigger. However, we have decay if our base value is between 0 and 1, such as this case here where our base multiplier was 1/2. If I multiply by a half, I continually get smaller and smaller and smaller. So those are the two types of situations we will see when we graph quadratic equations. Exponential equations. We will have growth and we will have decay. So this is the general form or general shape that we get when we graph exponential equations. What we're going to take a look at in the next lesson is what happens when we add vertical and horizontal shifts.